Have you ever stopped to think about what's happening right down at the atomic level? Not just, static atoms, but this constant, minuscule dance they're doing. It's like this whole symphony of vibrations that's usually completely invisible to us. Well, today we're doing a deep dive into some really groundbreaking science that's, well, for the first time, actually let us see into that hidden world. Our mission today is to unpack this new research breakthrough. They've directly revealed these incredibly subtle atomic vibrations inside these super thin, kind of twisted materials. So we're going to explore what these materials actually are, get into the really clever methods scientists use to finally spot these, well, tiny jiggles, and crucially try to grasp what these findings really mean for the future of materials science and all the tech that comes with it.
Yeah, and it's not just any old vibrations we're talking about here. These are a very specific type, something that's been theorized for ages called moiré phasons. They're a special class of what are called moiré phonons, things scientists predicted, but could never really visualize directly. And the fascinating thing is, even though they're tiny, these unseen motions can have a really big impact on how a material actually behaves, affecting everything from conductivity to its thermal properties.
Okay, so to really get what they found, we probably need to understand these twisted two-dimensional materials first. What exactly are we talking about? So picture taking two sheets of material that are unbelievably thin, like just a single atom thick. Graphene is a famous example, right? Known for being super strong, conductive.
Right.
Now, imagine stacking those two sheets, but instead of perfectly aligning them, you give one just a tiny, tiny twist, like a few degrees maybe?
Exactly, just a slight rotation.
And that slight twist is what creates these twisted two-dimensional materials. And the specific one in this study was tungsten diselenide, the WSe₂.
That's the one, WSe₂. And when you introduce that little twist, something pretty amazing happens structurally. You get this repeating pattern forming, which is called a moiré superlattice.
Ah, like when you look through two fences kind of misaligned, that sort of effect.
Exactly like that, that shimmering pattern. So in the material, this twist creates different kinds of regions. You get areas where the atoms are highly aligned. Scientists call them AA stacked or AB stacked regions. But alongside those, you also get these subtle structural faults or wrinkles, you could almost say. They call them solitons.
Solitons. Okay, so not just random flaws.
No, not at all. They actually form this really precise repeating network across the material. And it's this, this delicate arrangement of the aligned bits and these structured faults, the solitons, that really dictates the material's unique properties. These variations are absolutely key.
Okay, so we've got these cool twisted materials with their moiré patterns and solitons. Now, let's talk about the hidden vibrations, these moiré phasons. You mentioned moiré phonons are linked to this superlattice structure, but phasons are, what, an ultrasoft class of those?
Yeah, ultrasoft.
What does ultrasoft actually mean here? Low energy.
Extremely low energy.
Yeah.
And very low frequency. The predictions were around 0.1 inverse centimeters or maybe 0.01 millielectron volts. Tiny amounts of energy.
Right. So subtle they'd be almost impossible to pick up with standard techniques.
Precisely. That's why they were hidden for so long.
So why are they so important then, if they're so subtle?
Well, that's the fascinating part. Despite being so low energy, these phasons are predicted to couple strongly to really important physical properties of the material. If you sort of zoom out, these tiny jiggles can have massive consequences. Like they can significantly influence charge transport, basically how electricity moves through it. Crucial for electronics, right?
Okay, yeah.
They're also thought to play a key role in unconventional superconductivity. Getting materials to conduct electricity with zero resistance, ideally at more practical temperatures, that's a huge goal.
The holy grail, basically.
Pretty much. And beyond that, phasons are predicted to be the reason behind superlubricity.
Superlubricity, like zero friction.
Almost zero friction. Imagine materials sliding past each other effortlessly. Think what that could do for machines, engines, even medical implants.
Wow. Okay. What else?
Well, they also impact things like thermal conductivity, how heat flows, and specific heat at low temps, how it stores heat, basically. And even down at the level of how energy itself moves through the material, they can alter excitant diffusion. So they're involved in a lot of fundamental processes.
Okay, so hugely important theoretically, but here's the catch, right? Actually seeing them. You said they were extremely difficult to access experimentally.
That was the major hurdle, yeah.
Their super low energy just put them out of reach of conventional spectroscopic techniques.
Exactly.
Yeah.
It's like trying to hear a pin drop in a hurricane. Scientists knew they should be there based on the math,
Yeah.
but directly observing them. That was the challenge. No existing tool was quite right.
So if the usual tools couldn't see them, what changed? What was the breakthrough? The magic bullet?
The solution came from a technique called electron ptychography.
Ptychography.
Yeah, it's a pretty sophisticated computational imaging method. And it turned out to be this powerful new route for measuring atomic vibrations with incredible precision.
How does it work? Is it like a super-powered microscope?
Kind of, but it's cleverer than just magnification. It basically reconstructs a high-resolution image from overlapping diffraction patterns. So imagine you take a really, really fine beam of electrons, like atomic scale fine,
Okay.
and you scan or raster that beam across your material sample. As the electrons hit the atoms, they scatter, creating these complex patterns, diffraction patterns.
Right, like light through a crystal.
Similar idea, yeah. But instead of just taking one picture, ptychography captures these patterns from lots of slightly overlapping spots on the sample. Then, powerful computer algorithms take all those patterns and essentially piece them together, like solving a massive, incredibly complex jigsaw puzzle.
Ah, okay. Computationally intensive then.
Very. But the result is an image with ultra-high resolution. We're talking less than 15 picometers.
Picometers, that's unimaginably small.
It is. It's actually the highest spatial resolution of any real space imaging method we have right now. And that extreme resolution is the key. Because it's so high, the natural thermal vibrations of the atoms actually cause a measurable blur in the atomic images.
So you can see the effect of the jiggling.
Exactly. You're not seeing the vibration itself in real time, but you see its average effect, how much space the atom is moving around in. And they even refined it further using something called multi-slice electron ptychography, or MEP. Yeah, that helped them get more like a 3D map of how the electrons scattered, giving them depth information. And they used another algorithm, the extended depth of field, or EDF algorithm, to sharpen things up even more, cut through noise.
So a whole suite of advanced techniques working together.
Absolutely. These are crucial steps to finally resolve those really subtle atomic movements.
Okay, so they have this incredible tool. They pointed at the twisted tungsten diselenide. What did they actually see? You said they could image the size and shape of each atom and get these time-averaged vibrational amplitudes.
That's right. They weren't just getting static pictures. They could measure how much each atom was vibrating on average.
And did it match the predictions for phasons?
It really did. They observed several signature properties of moiré phasons. Clear evidence.
Like what? What were the key findings?
Okay, so first they saw increased vibrational amplitudes, meaning bigger vibrations, specifically at the solitons and also in those AA-stacked regions.
Ah, so those fault lines and aligned spots are where the action is.
Exactly. They're like hotspots for this vibrational activity. It tells us those structural features are really important dynamically. Second, and this is really telling, within those solitons, the vibrations were anisotropic.
Anisotropic
Meaning they vibrated more strongly in one specific direction, and that direction was aligned parallel to the soliton direction, like they were vibrating along the wrinkle.
Okay, interesting. And what about other areas?
Well, in contrast, in the AB regions, the other type of aligned area, the vibrations were shorter and more random in direction. They were isotropic.
So a clear difference in behavior depending on the local structure.
A very clear difference.
Yeah.
And that specific directional vibration along the solitons, that was a major confirmation of the theoretical predictions for moiré phasons. It behaved just as expected.
And they double-checked this.
Oh, yeah. These experimental results were totally consistent with the predictions, and they further backed it up with complex computer simulations, both molecular dynamics simulations and harmonic lattice dynamics calculations. Everything lined up.
Did the twist angle itself make a difference? You mentioned twisting it just a few degrees.
It did, yeah. They looked at that too. At really small twist angles, like less than 2 degrees, these lattice reconstructions, the solitons and stacking domains, really dominate the structure. And that's where you see these clear, localized phasons.
Okay.
As you increase the twist angles, say between 2 and 6 degrees, the phasons start to lose their localization. They become less tied to specific spots.
They spread out more.
Kinda, yeah. And then if you go to larger angles, over 6 degrees, the layers start acting more like 2 separate sheets of material again. The strong interaction that creates the distinct phasons fades away.
That's fascinating. So the twist angle is like a knob you can turn to tune these vibrational properties.
Essentially, yes. It shows how sensitive these effects are to that precise geometric arrangement.
So the big picture then, what does it really mean that they've finally seen these things? This isn't just theory anymore.
No, it's direct observation. They've, quote, directly imaged the moiré phason modes and their impact on thermal vibrations.
It feels like discovering a hidden gear in the machine of matter, doesn't it?
That's a great way to put it. And connecting it to the broader context, this work is much more than just finding phasons. It really demonstrates a powerful route to image thermal vibrations at atomic resolution in general, for any material, potentially.
So not just for these specific twisted materials.
Right. Think about understanding vibrations near defects, or at interfaces between different materials in a device. These are often where things fail, or where the crucial action happens. Being able to see how atoms are moving right at those critical spots, that's incredibly impactful. It gives us a whole new level of understanding for predicting how materials will perform, how they'll age, how they might fail.
Which leads straight into practical applications, I guess.
Absolutely. If you can understand these atomic movements with such precision, you can start thinking about designing materials with specific functions in mind. Like creating materials with tailored properties for better charge transport. Think much more efficient electronics, faster computers, phones that use less power.
Okay, that's huge.
Or pushing forward on unconventional superconductivity. Maybe this understanding helps design materials that superconduct at higher, more achievable temperatures. That would change everything for power grids, medical imaging, transport.
Oh, and the super lubricity thing. Zero friction.
Exactly. Imagine engineering surfaces with almost no friction for, well, anything from longer-lasting artificial joints to incredibly efficient engines and turbines, reducing wear and tear, saving energy.
It sounds almost like science fiction.
It does. But this brings it a step closer. And also controlling thermal conductivity. Designing materials that manage heat perfectly, whether you need to dissipate it quickly, like in powerful computers, or insulate against it.
So manipulating materials right down at the jiggle level.
Pretty much. And that brings up another important point. What about the technique itself?
Right, the electron ptychography.
Yeah. Its ability to accelerate understanding of dynamic material behaviors at atomic resolution isn't limited to just vibrations. It potentially opens the door to looking at other really subtle but crucial atomic scale properties. Things like charge transfer between atoms vital for batteries, solar cells, catalysts. Or magnetism. Or magnetic order, exactly.
Yeah.
Which is fundamental for data storage, sensors, and potentially quantum computing. The next big challenge technically is pushing this into 3 dimensions, getting that full 3D picture of atomic dynamics.
So this work has this amazing dual impact then. They've uncovered this hidden physics actually seen the phasons.
Right.
But they've also showcased and refined a tool, this electron ptychography, that could genuinely revolutionize how we study and even design materials from the atom up.
That's a perfect summary. It's an advance on both the fundamental science front and the materials engineering front.
It really is just mind-boggling to think about that level of precision. Zooming in on single atoms and seeing their minuscule vibrations, we're moving past just static pictures to understanding the actual dynamic dance of matter.
It's a huge leap, and it makes you wonder, what comes next? Imagine the possibilities if we get to a point where we can not only see, but maybe precisely control the jiggle of every single atom.
Control the jiggle.
Yeah. How might that fundamentally change the materials we can build, the technologies we can create? Think about quantum computers or targeted medical devices, or maybe completely new ways to handle energy.
It really opens up a universe of possibilities, doesn't it? Definitely something to think about how much more is hidden down there at the atomic scale and how finding it will keep reshaping our world.